Welcome back. In the last segment, we compared the advantages and disadvantages of the three major orbital regions around Earth. And in this segment, I want to go on a short side quest to point out a few special orbital types that you're likely to hear about in the news or elsewhere. First, we will discuss polar orbits, which are useful in mapping the Earth's surface. Next, we'll consider sun-synchronous orbits, which are actually a special type of polar orbit. And finally, we'll briefly discuss and name the region beyond geosynchronous orbits. Okay, so first let's focus on polar orbits. As it sounds, a polar orbit is any orbit that goes over the poles of Earth. And while such an orbit can exist at any distance away from the Earth's surface, in practice, polar orbits refer to satellites in low Earth orbit, usually 600 to 1,000 kilometers from the Earth's surface. Polar orbits are super valuable when you want to map the entire Earth's surface in detail. In fact, polar orbits are the only type of orbit that can map the entire surface of Earth. And imaging from low Earth orbit provides much sharper images compared to more distant MEO or GEO orbits. So to figure out why polar orbits are so valuable, we need to come back to the idea of orbital inclination. Orbital inclination is how tilted an orbit is relative to the Earth's equator. So a satellite with zero inclination is orbiting in the direction of the Earth's rotation just above the equator. These are called equatorial orbits. Inclined orbits have some positive inclination relative to the equator, so they travel above and below the equator over the course of one orbit. And a polar orbit has 90 degrees inclination. It moves perpendicular to the equator, going over both the north and the south pole over one orbit. And here's where it gets interesting. So, suppose our goal is to get a detailed image of the Earth. From low Earth orbit, we do get super detailed images, but at the cost of only being able to see a small portion of Earth at one time, just a few percentage of the Earth's total surface in one image. Imagine a satellite in equatorial orbit. As the satellite orbits, it's seeing a small ribbon of Earth. And even though the Earth is rotating underneath, it can still only see that small ribbon around the equator. Now, consider a polar orbit. Over a single orbit, the satellite still sees a small ribbon of Earth. However, we're in low Earth orbit where the orbital period is 1.5 hours, way less than 24 hours of the Earth's rotation. What happens in a second orbit? Well, okay, the satellite still sees a small ribbon of Earth in the second pass, but now the Earth has rotated underneath by 1.5 hours. It's seeing a different part of the surface. And over the course of the day, roughly 16 orbits, a polar orbit can map roughly the whole Earth. It's like wrapping a birthday gift with a thin strip of ribbon. Only polar orbits can map the full surface. We've already seen that an equatorial orbit just sees the equator, but let's look again at inclined orbits. What part of Earth is missed by an inclined orbit? As the Earth rotates, an inclined orbit can map all of the region up to its maximum inclination, but it misses the region above and below this, the polar regions. So an orbit that's slightly inclined can map only a wide region around the equator, while a more inclined, more tilted orbit can map a much larger area, but always misses the poles. So again, a polar orbit is the only way to map Earth's full surface, and for this reason, it's a super valuable place to put satellites. Okay, another special kind of orbit that's worth mentioning are sun-synchronous orbits. Sun-synchronous orbits are a special type, a subset of polar orbits. And like polar orbits, sun-synchronous orbits are low Earth orbits that go over the Earth's poles and so can map the full Earth's surface. But what's special here is that sun-synchronous orbits will pass over any given point on Earth's surface at exactly the same time every day. And if your goal is to monitor or compare a part of Earth over time, it's really nice to have consistent lighting and sun angle. So, for example, if my satellite passes over, say, New York City every day, a random polar orbit might go over at 10 a.m. one day and then 3 p.m. a few days later. A sun-synchronous polar orbit will always pass over New York City at the same time, say 9 a.m. And if the goal is to compare features in an image, it's just easier to have the similar lighting from day to day. Or if the goal is to monitor air pollution over the course of a year, it's crucial to take measurements at the same time of day to control for daily patterns. Okay, so far we've focused on orbital regions and special orbits around Earth. And the most distant orbit we've discussed is geosynchronous, which is out at like 35,000 kilometers from the Earth's surface. We know from Kepler's law that the orbital period of a satellite increases as we go farther out from Earth. So moving from geosynchronous with an orbital period of 24 hours, we can go much further out and come to another one of Earth's satellites, the Moon. The Moon is a satellite of Earth with an orbital period of 27 days, and the Moon is out at 400,000 kilometers from Earth's surface. There's a huge region of space between geosynchronous and the Moon. This region is called cislunar space. And while cislunar space is pretty empty at the moment, it's likely that there'll be increased activity in the coming decade as many countries turn their attention back to the Moon. We've now completed our side quest, covering polar orbits, sun-synchronous orbits, and cislunar space. Next segment, we'll wrap up this module, summarizing what we've done so far and previewing what it'll take to launch into all these different orbital regions.